Let's have a look briefly at the phasor signals in RC circuits. I won't cover the LR circuits here, but the basic ideas are exactly the same. We'll start with a series RC circuit as shown in the diagram. Here, as we discussed in some of the previous videos, the current is constant through all the components. There's nowhere else for it to go, so it must flow through each one. But the voltage across each component can be different. We already know the resistance of a resistor, but we now need to work out the reactance of a capacitor using Xc equals 1 over omega c or Xc equals 1 over 2 pi Fc. Now the current flowing through the circuit is opposed by both the resistance and the reactance. We can combine them together into an overall effect which is called impedance. However, because the phases of V and I are different in the resistive load compared to the reactive circuit, we can't simply just add them together. They have to be combined as shown below, with Z equals the square root of R squared plus Xc squared. If there was also inductance in the circuit, the formula would be modified as shown below. An example will make this a little bit clearer. So let's put in some values. Let's say that Vs is 10 volts, that the resistance is 5 ohms, and the reactance, which we used the formula previously given to work out, is 2 ohms. Then Z is equal to 5 squared plus 2 squared, square rooted, which is equal to 25 plus 4 square rooted, which is equal to the square root of 29. Now we are in a position to calculate the current through the circuit using I equals V over Z, Z being the impedance, which is equal to 10 divided by the square root of 29, which is equal to 1.857 approximately. And so, having worked out the current which is flowing through all the components, we can work out the voltage across them. The voltage across a resistor is simply given by V equals IR, and across a capacitor by Vc is equal to I times Xc. But to see what's really happening, let's draw a phasor diagram. Because the current is constant, let's draw it along the x-axis. Now, the voltage across a resistor is in phase with the current through it, but the voltage across a capacitor lags the current by 90 degrees. We can draw this in on the diagram. And from this information, we can construct the voltage across the power source, which will be the resultant of these two voltages as shown in the diagram. From this and simple trigonometry, we can work out the angle between the current and the voltage of the supply. Let's call it theta. Incidentally, the cosine of this is sometimes called the power factor of the circuit. So having looked at the series circuit, let's now look at the parallel RC circuit. This time the voltage is constant because it's been directly applied across each component, as we explored previously. But the current in each branch is different this time because it divides down the different branches of the circuit. The current down branch 1 is the voltage divided by Xc, and the current down branch 2 is the voltage divided by the resistance. And so we can draw the phasor diagram as shown below. So IT leads VT in this particular case, and we can work out the resultants and the angles just using simple trigonometry.